We have vectors, the data, now we need something that acts on them. That something is a matrix. It looks like a boring grid of numbers, but its true meaning is dynamic and beautiful. A matrix is a transformation of space itself. Let's see it move. Here is a matrix, a grid of numbers, arranged in rows and columns. You could think of it as just a table. But watch what it does. When a matrix multiplies a vector, it moves that vector to a new place. Feed it every point in the plane and the whole space stretches, rotates, or shears. A matrix is a verb, not a noun. It does something. Here is the key to reading any matrix. Look at its columns. The first column tells you where the basis vector pointing right, I hat, lands. The second column tells you where the basis vector pointing up, j hat, lands. Once you know where those two arrows go, you know where every point goes. The columns are the whole story. So how do we apply a matrix to a vector? It is a simple recipe. Take the vector's first number and multiply it by the first column, take the second number and multiply it by the second column, then add. The vector is just a set of instructions, this much of the first column, that much of the second. Multiplying is following those instructions. Let's watch a real one. Take the matrix with 2 and 3 on its diagonal. Its first column sends I hat to 2, 0 twice as far right. Its second sends j hat to 0, 3 times as high. So the whole grid stretches, twice as wide, 3 times as tall. Every point moves, but the grid lines stay straight. Different matrices do different things. One matrix rotates the entire plane about the origin, spinning every arrow by the same angle. Another shears it, sliding the top sideways like a deck of cards. Reflection, projection, stretch, each is just a different set of columns, a different destination for I hat and j hat. Why do we call these transformations linear? Because they follow two strict rules. Grid lines stay perfectly straight and evenly spaced, and the origin never moves. No curving, no bending. That rigidity is exactly what makes the math so clean, and why linear algebra is the foundation of so much machine learning. There is one special matrix worth meeting, the identity. It has ones on the diagonal, zeros elsewhere. Its columns send I hat and j hat right back to where they started. So it changes nothing at all, the do-nothing transformation. It is the number one of the matrix world. And here is why this matters for machine learning. Inside a neural network, every layer multiplies your data by a weight matrix. Each layer is a transformation, reshaping the data into a new representation, untangling it, stretching it, until the answer becomes easy to read. Learning is just finding the right transformations. So, matrices. Not tables of numbers but transformations of space. Read them by their columns where I hat and j hat land. Stretch, rotate, shear, each is one matrix. And every layer of a network is one of these transformations. Next, what happens when we do two of them in a row? Chapter 6, Matrix Multiplication.